Recording. So, how did you find the assignments 6 and 7 about the symmetry?
It's okay, sir. But about this molecule, this they are asking about the symmetry of certain kind of molecule.
Yes.
That was that thing. I'm not that much familiar with that. But
Okay.
uh,
Like in
okay,
assignment, that ClF3 kind of molecule, right? So we'll try together and see how to start with. And I think you need to know the basics, but when you know the basics, then you will be able to do it. So from where one wants to start. Okay. Now, let me welcome you to the week 8 live session of molecular spectroscopy, a physical chemist perspective, the discussion sessions. Um, so I will not write anything. I have written something. I will just by animation it will disappear and one by one notes are come. So first let us start with as we are discussing. So first of all, why symmetry is going to require because in the later half of the course till now we have dealt with some diatomic molecules, homonuclear diatomic or heteronuclear, but in the later half we are going to deal with the electronic transition of something like benzene, some very big molecules. Not big to be honest when we work with some very big organic molecules, but in case of means spectroscopy, if you want has to know the solve the Schrodinger equation for benzene, then it's actually one cannot do it in pen and paper. With pen and paper, one need computer and computing facility. So actually this to know symmetry and those energy states transition that will go hand in hand. That's why we have to know symmetry to understand the transition what are going to be happen in the mainly in the polynuclear or polyatomic molecules. So to start with, we have the symmetry elements. Symmetry elements are those upon which we perform the symmetry operations. Like identity is common. It is going to be everywhere. Identity is noted by E. Then there is some rotational element, rotation. So upon some axis, which is mainly known as principal axis, even there are some secondary axes are also going to be there, upon which the rotation can be done. So Cn, n denotes for 360 degree by
mm,
theta by n
exactly. Yes. Yes.
by n. So that
Yes.
is
Yes.
your angle of rotation. So
Yes.
it can if it is C2, then you are rotating by 180 degree. If it is C3, then you are rotating by 60 degree. If it
120
is
degrees.
120 degree, if it is what do you think of benzene? What is the principal
Engine
axis is
C6,
going on?
C,
C6.
C6,
So
C2, C3, all these are there.
yes,
The
all this rotational axis is going to be there, but C6 is the principal
principal
rotational.
rotation. Yes.
So that actually deals with a rotation of 60 degree, 360 by 6. Now there can be reflection along some planes. Now this reflection can be along some vertical planes, but what are vertical planes? That
What
contain
contains the principal rotation axis.
principal rotation axis. And then there are something called dihedral angles. So
Yes.
upon which those are sigma d kind of thing, right?
Yes.
Now another symmetry element is possible. That is point of inversion. Obviously, for centrosymmetric molecule, you may have I. I is point of inversion, along which you can it can be symmetric it some symmetry species it may not be symmetric depending on that if this symmetry inversion I may not be there in everywhere, right? So the actually which symmetry elements are there in a molecule will determine it point group, right?
Yes.
So
Yes.
that's the starting point. Now symmetry operation that based on these elements we are going to perform some this element based on these elements we are going to perform some experiments or operation, and that is going to give me a equivalent structure. Suppose H2 is there and we already know there is if I perform identity operation E, then it is doing nothing, it's just like that. If I am performing a C2 on a H2 molecule, then just it is rotating, but at the end of any symmetry operation, we are going to get equivalent structure. See, there the H2O you can think of as a H1 oxygen H2. There are two hydrogen.
Yes.
But when we perform some E, suppose identity operation, it remains H1O H2. But suppose I am applying C2, C2Z,
Yes.
then you are going to get H2O H1, but still the structure remains equivalent. That's the funda of symmetry operation. So we'll apply the symmetry elements and we are going to get equivalent structure. Suppose a molecule doesn't have a point of inversion as a symmetry element, then you can't operate it on that molecule. So that symmetry element is not there. That means you have to see that that point group may not be for this molecule. Anyway, and there are some known as bases, so on which your symmetry operations will be performed. It can be your Cartesian coordinates like x, y, z. It can be your atoms. It can be wave functions. It can be orbitals. It's a wave function of the orbitals, obviously, and it can be anything. And that's why even so some quadratic functions, it could be some linear functions, it could be some rotational function, so it could be anything, the basis could be anything. So that's where we will later going to discuss the character table. But your symmetry operations are those where the symmetry elements we are going to operate it on this basis. And this is the example of H2O where the point group is C2V. How do we know it? See, there, this is what I was saying, that it is, let me go to my laser pointer. So maybe a different color. Do you have? We don't have a different color. So this is Ha, oxygen, Hb. Now think of this as it is there on some plane of my laptop or plane of my paper, and that plane is XZ plane, and there your principal axis of rotation is along z axis. So first of all, when we are going to determine the point group of any molecule, first we have to see if there is any CN axis, can we rotate it. Obviously identity is always going to be there, but if there is any CN axis is there or not. So when we look at H2O, we know yes, there is a C2 axis of symmetry. Now let us put z axis along. So see this x, y, z, these are arbitrary, so we can put it as per our need. So there is it is not fixed that z is going to be only along this direction. It's not like that. So this what we are putting it at our preferences. So because as we know that your C2 axis is working on this side, so we are saying okay, let us keep this as z, and other perpendicular axis will follow. Okay. Now, suppose this is x, this is y. This could be minus y minus x. So the please check it accordingly. But this is going to be the y-axis. This is x. Now, what I'm trying to say that C2 is along z. Now you see there are two vertical planes. Why I'm saying vertical planes? Because this is containing the z-axis, which are those xz and yz.
Yes.
Yes. Along that, you can see you have some reflection plane is there,
Yes.
and those elements will lead to your equivalent structure. So these are the four things. So first, what you see, identity is there, C2 is there, and now sigma v's are there. So even if you are confident that you can see one sigma v, you don't have to find the second sigma v. Okay, because then means suppose the a very complicated structure, you can see the cn axis, one sigma v axis, and do not have to find another sigma v, it would be cnv. Okay, means what I'm trying to say is giving you hints for the some later problems if you have to find some point group of any molecule. Okay, now suppose after finding C2, you are seeing that there are some so along with the principal axis of symmetry, there are some cn axis which are perpendicular to it. Then you are going to go to the D point group, D2, DND or DNH, right? You are going to lead to those point group. I think Datta sir has already provided you
Table was there, yes.
yes, a scheme
Big,
of
very
that.
big.
So
Yes.
one need to follow that step by step. But for this simple molecule like H2O, NH3, even the one that is given in the assignment, you don't have to work that much. By looking at this, I think you are going to tell that what point group it is. Anyway, like suppose CH4, methane looks like a very simple molecule to start with, but when you are going to, obviously you know it's tetrahedral, but you are going to see the point. There are a lot of symmetry operations are uh, included with each other. Anyway, so for each these symmetry operations, you are going to get some transformational matrix, and you already know that suppose you are taking your basis set as xyz, then you are going to get some your transformational matrices like this. For E, you have 100 010 010 C2Z is going to follow the same -10 0 -10 0 0 0 1. Anyway, so this is the basic, and then so that is there. Now you see, when you take your basis as XYZ, you are going to lead to your transformational matrix like 100 0 1 and you can
Block
block
factorize.
factorize it. But when you take your atoms as your basis set, then you are going to see that earlier it was something like one dimensional representation you are getting. Okay, each of these were one dimensional, but when you take your atoms as basis set, now you see that your this when you block factorize, you are going to get a one dimensional one and a two dimensional one representation. So wait, I think now these are called actually representation. These individually one minus one one. These are symmetry spaces. To be honest, it could be irreducible and it could be reducible. What do I mean by reducible? That means you can still break it into some of the irreducible representation. And the irreducible representation, obviously, you can think you can understand by its name that you cannot reduce it into further, but reducible
Yes.
you can it. But see, when you have this kind of representation, you still don't know if it is irreducible. Suppose this two-dimensional representation, when you get it for the when you took the basis set as your atom, you are getting some representation like this. You don't know yet if this is a reducible or irreducible representation. And to know that, and you can see that when you are changing your basis set, your representation is changing your. So obviously the totally symmetric one means 1 1 1 1 for here. So this is called totally symmetric representation. That representation is always there, but you can see that suppose instead of uh, so tell me one thing. Suppose this is a H2O molecule, right? Three atoms are there. What are the other bases you can think of? Can you tell me some other bases? What you can think of?
This what are the other bases? Let's say uh, S S orbital can be taken
S
as
orbital. So what do you think? S orbital, what is going to be the, so if you take a
these are
S orbital,
spherical. That will
they,
leads to same product OH1 H2.
right. And right. So in that case, suppose when you take a basis set with these three s orbitals, one belongs to H1, one belongs to H2, and obviously you are talking about, as you are talking about hydrogen and then oxygen, maybe you are talking about the 1s orbital only so far. Now,
Yes.
suppose I am asking you to think of it as a 3p orbitals, not 3p. Suppose for H2O it is. So, what do you think? For hydrogen, is there any p orbitals exist?
No, 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 no.
What if I
If it is in excited, if it is in excited state, then it may.
right? So,
Yes.
so suppose there are p orbitals which are vacant.
Yes.
Think of like there are 2px, 2py, 2pz. Okay, just think. Maybe you can think of some other molecule also. But
Yes.
if you take this, suppose even you don't have to go to 2px, 2py, 2pz. Suppose you are going to take the Cartesian coordinate for each atom, right?
Yes.
Suppose you are going to take x y z for h1, x y z for c2z, and h2 x y z. What do you think that how many what kind of transformational matrix you are going to generate from that basis set? So first of all, in your basis, how many rows are going to be there? If you take x y z for each of the atoms. Suppose you are
Uh,
taking oxygen, instead of oxygen you are writing OX, OY, OZ.
okay.
Suppose for H1 you are write H1X, H2, H1Y, H1Z. And for H2 you are writing H2X, H2Y, H2Z. So how many rows are there? You are taking nine
In
nine
total nine.
rows.
Total nine. Yes. Yes.
So what do you think your transformational matrix uh,
9 by 9.
each yes, each of the transformational matrix are going to be 9 by 9.
9 by.
So
Yes.
you can see that if you change your basis set, accordingly your transformational matrix is going to change, right?
Yes.
Means size of the matrix will change, but that doesn't give us the idea that how many irreducible representation it is going to have,
Yes.
because you can see 9 into 9, so maybe 9 irreducible representation, but that
Yes.
is not true for C2V, right? Because we
Yes.
know for C2V it has four
Ye-
classes.
Yes. Four.
Actually you
Yes.
have
Four.
already known the great orthogonality theorem. That's why you know that the number of irreducible representation is going to be the number of classes you have, but we will
Yes.
come to it later. So you don't know yet that how many, so which are irreducible representation, how to differentiate. So that's why next you are going to need that this is the thing I told you now, that the representation will depend on the basis and different representation for different basis set. And we don't know how many number of reducible or irreducible representation is going to possible. So for that you are going to need this great orthogonality theorem, GOT. Uh, this is the equation there. Sum over R. R is our different symmetry operations. So, and then you have gamma I R mn multiply by some complex conjugate of gamma j r m dash n dash equals to h by root over li lj, and then some Kronecker delta function, delta ij, delta mm dash, delta nn dash. So actually this will come. So as I have told you that Professor Datta has a different course also there on symmetry and group
Yes.
theory. There this GOT was actually derived.
Yes.
So, but we don't, for these codes, we don't really require that. We need the essence of it. So, first of all, what is the fast in the left hand side? What is the fast term means? That gamma I R mn. That means your m and n is m is the m tells you about the row, and so so we have all transformational matrices, right? So now
Yes.
think of a matrix, one of the transformational matrix, and there you go to m row, mth row, and nth column. Then for a specific symmetry operation. So that operation is R. So
yes,
for a symmetry for a transformational matrix for R symmetry operation, you are going to this matrix element. So mnth matrix element of the transformational matrix of symmetry operation R in the ith irreducible representation. Then and similarly, gamma j is jth irreducible representation, and H is the order of the group, point group you are dealing with. For C2V it is 4, for C3V it is 6. And how can we calculate it? The number of symmetry operations. Okay, so suppose for C2V, what are the symmetry operations? E, C2,
E sigma v, two
yes,
sigma v, sorry.
2 sigma V.
Sigma v, mm,
And those two sigma phi are of similar order, similar same class or different class?
different classes. One is in
Different
the plane.
classes, right? So the total, the symmetry of the number of total symmetry operation is 4, and class is number of class is 4.
Yes.
What about C3V? How many number of operations are possible, symmetry operations, and which what are they?
C3v, there is C3 is there, E is there, then
Yes,
C2 will, C2 no C2.
no
Then
C2.
not C2. Then
Think of it as think of it as NH3 NH3 molecule. Well, suppose let me go here and let me write it
I think C2 is there
for
for
C3b.
NH. Yes, if it is NH3, then
Okay, let me draw. Suppose C3v, right? So we suppose this is H1, or maybe we can write HA. Then we have some out of the plane this HB, and suppose we have behind the plane HC, and obviously there is a lone pair. Okay, something like that. So now,
yes,
what is the principal? So E is always there. So E is
mm,
there. What is the principal axis of symmetry?
C3 is there.
C3 is there. So along this, can I say this is my Z axis, and you
Yes,
can rotate along C3. Okay, C3 is there. Then you are saying C2 is there. Can you identify that from where you are saying, or where do you think the C2 axis is?
let's say it is passing through NHB.
NHB. Okay,
Then your HA will be shifted to HC, and HC will be shifted to HA. Is
but
it
you have to
possible?
remember that each of these are uh,
Yes.
of 120
Each of
degree.
yes,
So do you think if you, for N and HB, you are rotating it by 180 degree, it is going to land on there on HC? I don't think so.
yes, that
It
will up.
will be somewhere, if I think of it out of plane, it will be something like here.
Yes, yes, yes.
So do you think, still think then
No, it
um,
will.
C2 is there? Actually, you are thinking in a correct way, but it is not C2. It's a no rotational axis, but think in terms of rotational plane. Think in terms of rotational plane. Then you, on the same bond, NHB, suppose
Yes,
you have a reflecting plane.
yes, yes,
Maybe think of it as, so first you have identity. So suppose you don't know it is C3b, huh? Suppose your NH3 molecule is given. Then you know E is there and C3 is there. Now you
yes,
try to find out any perpendicular uh, uh, C2 axis are there or not. But you can't find. So it is going to be some. either CN, either CNV or CND. Sorry, yes, CNV
Like
or
it.
another what is possible CNA.
Horizontal plane of symmetry, CNA.
Yes, suppose you still don't know that what is going to be there, but you know that it is going to be either C3 or C3V or C3D. Then you try to find out. You already sure that there are no perpendicular C2 or CN
Yes,
axis to your
yes,
C3. Now you try to see if there are any sigma V's are there. Sigma V will contain your Z axis or
yes,
C3. So
yes, yes, yes,
suppose this is your one of the plane. So this
yes.
contain your Z axis and this
Mm.
bond, right?
Yes. Three sigma
So
V's are there.
three sigma V's are going to be there.
Yes,
So and are they going to be equivalent or are they going to be uh, different?
yes, they are equivalent.
So sigma V, let me write then three sigma V altogether. So
Yes,
there are
yes,
three sigma V operations are going to be there.
yes,
And what do you think about C3? C3 you rotate it by once by 120 degree. So your HA, suppose let me draw it here. So when you do that, your this out of the plane become HA, this becomes HC, and this become HB, right?
yes,
Once one time perform C3 along these axis. Huh?
yes.
Can you perform another C3?
Then HA turns out to be HB. HB means it will rotate by 120 degree. HA becomes HB. Yes.
So your
HB becomes
HC
HC.
actually come here.
Yes, yes,
Your,
yes,
this will become your HB,
yes,
and this is going to be your HA. So another C3 is possible. So
yes.
so from the first position, how can you reach here? Either
C3 square
C3 square or
or
C3
minus
inverse
C3. Yes,
minus
yes,
C3, right? So there is another operation can be there, right? So 2C3 kind of equivalent to C3, right?
yes,
Is it making sense? So from here,
yes, yes,
whenever you can find that you see there is C3, there are no perpendicular C2, and there is sigma V, directly write the point group is C3V. Suppose, let me give you another example. So this is a pyramidal kind of a molecule, right? Suppose you
yes,
have BF3, okay? You have BF3, and this is a planar molecule. Okay, BF3 is
yes.
a planar molecule. So what do you think? What from where you are going to start? So it has obviously E is going to be there. What is the principal axis of symmetry you think here? Rotation, principal axis of rotation.
Yes, it is also C3.
It is going to
C3 is
be
there.
C3.
Yes. And
Okay.
here C2 is there. Here C2 is there
Two,
in this.
so there are two C3 going to be
Yes.
associated with. Do you think
No,
the
no, only one C3, but two this three C2 is there in this case because it is planar molecule. So if you are going to
uh,
pass one of the BM,
why do you think there are only one C3, no C means so you so suppose this is out of means I am coming uh, so the molecule is in the plane of the laptop in the screen and this
yes,
is I am looking at from top. So this is a
yes,
planar molecule. Now
yes,
suppose along the Z axis I can perform one C3 and C3 square also I can perform.
yes,
So,
yes,
so there are two C3, but the principal axis is obviously principal axis of rotation is C3. Now, what you are saying that is true, that perpendicular to this C3, do
Yes.
you have C2 axis or not? And how many C2 axis do you have?
Three C2 axes are there because three
Three
BF. Yes.
C2. And do you have a molecular plane?
Yes, yes, molecular plane is there. Sigma is there.
Sigma, no, that is not sigma xz. That is going to be sigma
H
xy.
only. Yes, yes, sigma H or
Because
sigma.
your
Yes, yes,
z is pointing towards us. Huh?
yes.
So we have xy
Yeah,
in the plane.
I was saying sigma H. Sigma H
Sigma
is equal to
h.
sigma X XY.
True, true, true. You are correct. So you have sigma h also. What else do you have here?
What else? I have also yeah, sigma V is also there.
So there are three sigma v's.
Yes, yes. Three sigma V's are there.
Do you have any? So do you
I have
have a?
also
Do you
sigma
have
D.
sigma d? Do you have?
Sigma D. Yes, C2 is there. And C2 is
Isn't
there. I think.
isn't those are the sigma v's?
Yes, I think so.
Okay. Now think if there is point of inversion is there or not?
Point of inversion, no,
It's not there. So
no.
see. So what do you think this point group is of this molecule so far from this idea? So it has a C3 axis.
Yes,
Then we have three perpendicular C2 axis.
yes.
Then itself it has become D3.
D. Okay.
Now it also has a molecular plane.
Yes,
So it is
D3.
D3H.
So, as we have C3 as well as C2, that's why we call it D.
D. Yes.
Okay, okay,
If those perpendicular C2s are not going to be there,
okay,
then it would have been C3V.
okay.
And see, that is the difference. So this is also similar to NH3, just
Yes,
that this is a pyramidal kind of a structure. So you have to know certain idea about the
molecule.
VACPR theory. So
Yes,
from there you have to know that this molecule is planar, this is pyramidal. Okay, and why this is
yes,
pyramidal? Because this lone pair is there. But in
yes,
case of BH3, nothing like that. So
yes,
you can even given the problem in one of the assignment that carbonate ion,
yes, yes,
right? Carbonate is 2 minus, I guess, or 1 minus
yes,
sodium carbonate. So CO3 2 minus. So how does it look like? It will look similar
and
as BF3.
yes,
Your the central atom would have been carbon, and this would have been oxygen. Okay, and one of two of the oxygens are maybe are going to have the negative charges anyway. Uh, so from there you can see that you have to know a little bit about the molecular VACPR theory, that what kind of structure it is going to have. So in case of ammonia, C3 was there, but no perpendicular C2 was there. That's why it was, even though you can see there, what are the difference? Here it has identity, it has two C2 axis, it had three sigma V axis also,
yes,
right?
yes,
But it
yes,
did not had the molecular plane as well as the perpendicular C2. So that's why
yes,
it was C3V and this is D3H.
yes, yes.
Okay. So let us come back to here. So here what we were discussing, we are discussing about the great orthogonality theorem. From we already, so where we are going to require this, we from to solve a few. So how can we understand that the question was that how to differentiate a reducible and a irreducible representation, and there this great orthogonality theorem comes handy. So we have a molecule. We already determined its point group. So we know the symmetry operations it has, right? So
Yes.
from there on, we are going to build the character table for this molecule, and for that, each of these transformational matrix of those symmetry operations are going to be required. Now, suppose what are Li and Lj? Li and Lj are the dimensionalities of this ith and jth irreducible representation. So, uh, of a one-dimensional irreducible representation, Li would be 1. For a two-dimensional irreducible representation, it is going to be 2, and for a three-dimensional, it is going to be 3, and so forth. And H is the order of the point group that tells us how many symmetry operations are there. Now tell me, for this molecule, D3H, how many symmetry operations are there?
Total one E, two C3, three C2, sigma H and D. 1, 2, 3, 3, 6, 10, 10, total
10
number,
is
10
there,
numbers.
right?
Yes.
And let us come to the this point group, not point group. We are discussing about D3H, right?
Yes.
D3H. So see, E is there, C3Z is there, 2C3Z, 3 perpendicular C2 is going to be there, 1 molecular plane is there, 3 sigma V is there. Not only that, 2
Okay. Yes.
improper axes of rotations are also there. What are these improper axes of rotations?
Rotation as well as reflection is there.
Yes, and why it is possible? Because you have a molecular plane.
Yes.
So you are rotating along. So you have two C3. So you rotate once C3, then uh,
Again, sigma H.
along this sigma H, you have a equivalent structure. Again, you perform C3 square, and then also you can perform the sigma H. So these are the two S3s are also there. So total actually 12 symmetry operations are there. Okay. So you can see the number of symmetry elements H is equal to 12. But see, for understanding a point group, you don't have to get all these uh, symmetry elements or symmetry operations. You don't have to know. You just see principal rotation of axis. See if there are any perpendicular C2 axis are there or not. Is there any molecular plane is there or not? Then it's easy, right?
Yes.
You don't have to know if S3s are there or not, because at the end of the day you are going to you will be given the character table. So for this course you don't have to mug up any character table. Okay. Okay.
Yes.
Now let us come back. So with this you can get, these are the 5 axioms you can get, that first of which is number of irreducible representation is going to be number of classes. Then the character of the transformational matrix of your identity operation is going to be your dimensionality of that irreducible matrix. Like for C2V, it can be 1, right? Now you see, you need to be very careful about that, upon what these summations are based on. Okay. So see, this is summation of character of E and whole square. You have character of E of a certain irreducible representation and take a square of it, and you do it for all the irreducible representation, then you are going, that sum is going to be your H. Similarly, you are taking only, so when you take a take sum over r, means the symmetry operation, then you are only talking about a single irreducible representation. You don't have to think of another irreducible representation, just think of one. And there what you can do, when you take the character of each symmetry operation and take a square of it and sum them up for all symmetry operation, for that also you are going to get the h, the order of the
Order.
point group. And the most important one, why this is called the orthogonality theorem, you can see that for two irreducible representation where I and j are different, so
They are normal to each other.
they are orthogonal to each other. If I and j are equal, then only they will show a normalization condition. If I and j are different, you think of this Kronecker delta function, I and
Yes.
j. So if I and j, I is not equals to j, then this delta ij is actually 0. Then your right
Yes.
hand side is 0. So your character of your one of the uh, one of the symmetry operation with the character of the same symmetry operation from a different irreducible representation, you are going to get 0. But how can you actually, so see, these are axioms, right? We are saying that this actually comes from this great orthogonality theorem. For this course, you could have just mug it up or just remember it, but I tried to give you the derivation. Actually, you can see it here. So I am going to show you the derivation, how you are getting that from this matrix element. How can you get the uh, um, character? How can you go up to that particular axiom? So first line is your just the same, your great orthogonality theorem, right? Gamma I Rmn gamma j Rm dash m dash is equal to this. So now you think of the same irreducible representation. Suppose we are going with gamma 1 only or gamma I, where your I equals to j. Okay.
Yes.
So your delta ij is going to be 1.
Yes.
Also assume that we are going to take this only the uh, diagonal only the diagonal elements of our transformational matrices. So for that case, your n is going to be m and
Yes.
n dash is going to be m dash. If I are
Yes.
only thinking about the diagonal terms of each transformational matrix, right?
Yes.
So then let us see how this equation transform. So it is sum over r gamma I r mm gamma I r m dash, okay, is equal to h over delta li into li, because we are taking the same irreducible representation. So lj has become li. So li dot li, it li square, so root of that is going to be li. And what else is there? The delta ij is already 1 because I equals to j. Now you think that your delta m dash, delta m dash, so it is actually delta m dash square.
Yes.
So it, so the maximum value could be 1 and the another value could be 0. 1
Zero.
1 into 1 could be 1 and another is 0 into 0, that could be 0, and another others are 1 into 0 and 0 into 1, so that would also lead to 0. So when m equals to m dash, it is 1. So you can also write it in terms of delta m dash. So delta m dash square, you can write delta m dash. And if we do that, what we are going to get? Next line, that delta I RMM same. Left hand side is same, just the right hand side I have changed. H divided by Li
And
into delta dash. Now taking sum over all m and m dash. So so we are talking about the diagonal elements. So there are multiple m and m dash. So
Mhm.
so from this line, suppose we are coming here, that sum over r is there. Gamma I r m m, gamma I r m dash m dash. But now we are taking all sum over all the m and m dash. See what is a character? Character is you are taking sum of all the diagonal elements.
Yes.
So that's why we are taking sum over all the m and m dash. So we are doing same for the left hand side, also the right hand side. So now think, now see, sum over r we are taking it outside, and sum over m gamma I over r mm, and sum over m dash over the gamma I r m dash equals to h by li sum of m dash gamma delta m dash, there. Now look at the left hand side only. What we got? Sum over r. Now see this sum over m gamma I r mm. So we are talking about the diagonal elements, and sum over all the diagonal elements is your character.
Yes.
So character of the ith irreducible representation your uh, for a particular symmetry operation. Similarly here also sum over mm dash gamma I r m dash. So for these also you are going to get the sum over all the orthogonal diagonal elements, and that is going to lead to your character of the same, right? So it is gamma I r, right?
Yes. That is.
And
Yeah.
that is equals to h by I, then your sum over m dash. So you now think of this of delta mm dash, and what could be delta mm dash when m equals to m dash. When m equals to m dash, it is going to lead to 1.
Yes. Yes.
And yes, and when you sum over them, you think you are going to get the dimensionality of that transformational matrix.
Yes.
So that's why it is going to be Li. So H over Li into Li. And here Li going to cut. So you are going to H. So this is not the orthogonality condition, but you see what you are going to get. This sum over R, character of your R, means the symmetry operation, square of that is going to lead to H. Now
Order.
think of the same. Now I not equals to J.
Then
Okay.
it becomes zero.
Yes, then delta ij is going to be 0 because I not equals to j. So your
Yes.
right hand side is 0 from the starting. But
Yes.
now see, if you take the same thing, you are going to lead to your chi of or character of ith irreducible representation and character of r in the jth uh,
It
uh,
is.
reducible, and that is going to give you the orthogonality theorem, that sorry, the orthogonal condition, that chi I of r multiply by chi j of r sum over all the symmetry operation, you are going to get 0. So from the I just wanted to give you the derivation how actually you lead to that these two. So you are already given these five working rules. So I just wanted to make sure you know that how can you derive it, the fourth condition and the fifth condition, right? I hope you get the point what I
Yes.
am trying to
Yes.
say. Yes. So now I'm not going into the deep of it. That this is the character table for the C2V, and this has been constructed using the GOT. And what are the first thing was that we have put the totally symmetric one. So there is always going to be one representation which is going to be the totally symmetric one. So that
Yes.
one has put it here 1 1 1. Now next was that we didn't know any other thing, but we knew that the sum of the square of the uh, uh, sum of the so first of all we knew that for C2B there are four different classes. So there is going to be four irreducible representation. So gamma 1, gamma 2, gamma 3, gamma 4. And we already written the first one, totally symmetric one. Then we knew that the what is Li? Li is the character of the identity
This operation.
operation, transformational matrix of identity operation character of that, and square of
Yes.
that is going to lead to us the
Order of
total
order.
order of the group. And for C2B the order of the group is 4 because there are 4 symmetry operations possible total.
Yes. Yes.
So from there what one has done, 1 plus chi2 e square chi3 e square chi fourth of e square is equal to 4, and you knew that they are all going to be 1. Your dimensionality cannot be negative. So
Yes.
either it could be 1, it could be 2, it could be 3. But you had three uh, unknowns, one equation, but you know that the value could be either 1, only
Mhm.
option is 1, right?
And the
Or
option is 1.
2 or 3. But that's why
2
you
is not
know
possible.
2 is
Yes.
not possible, only 1 are going to be possible, so all are 1. So
Yes.
you also written that. Now you have taken care of the rest of the term by this orthogonality of the characters of different I and jth irreducible representation. You mark them all, and you knew that out of these 4 1, 2 are going to be negative always. So you can write them up. And you also have the Mulliken nomenclature, and by which you can give each of them a name. Gamma 1, gamma 2 is irrespective of gamma 1, gamma 2, gamma 3, gamma 4, you can give them name. And what are the procedure? That for one dimensional representation,
Can only take A or B.
one or two, sorry, uh, A and B. And how can you make sure that it will be A or B? That you need to
With
check
respect to
this.
C2 operation.
Yes, with respect to the C2 operation. If it is symmetric, then A. It is antisymmetric, then B.
B.
How can you say if it is 1 and 2? You need to look
1.
at the next symmetry operation.
Yes.
Okay, for C2V, it is sigma V. You can see that sigma V, the first one is total, it is symmetric with respect to sigma V XD, but it is not, it is antisymmetric with respect to sigma V, the second one. So the first one is A1 and second one is A2. Similarly, uh, the gamma 3 and gamma 4 are named as B. But when they are B1, so your gamma 3 is symmetric with respect to sigma V, but gamma 4 is antisymmetric with respect to sigma V. So that is why it is B1 and B2. Okay. And
Yes.
you don't need any other identifiers or symmetry elements, so that we had stopped at A1, A2, B1, B2 because we have we can distinguish them now. But suppose you have some D6H or some very big point group which have multiple irreducible representation, then you are going to need some other uh, Mulliken nomenclatures also. Like if the character is one, if your if your reducible representation is symmetric with respect to the molecular plane, then you can put single dash, and if it is antisymmetric, then you can put double dash. Similarly, if it is and your irreducible representation is symmetric with respect to the inversion point of inversion, then it is you can write Gerard G. And if it is antisymmetric with respect to your I, then you can write Ungerad, U.
You.
So these are the other identifiers it will come. Like for C3V, you can see A1, A2 and E. But the difference between C2V and C3V, what we can see is there for C2V, all the irreducible representations were
One
your
dimensional.
one dimensional. But your C3V, we are fast introduced to a to say two dimensional representation. And not only that, in this character table, in this side you can see these are bases, right? X, Y, Z, how your X, Y and Z transform along these individual symmetry operations lead to that which symmetry species they belongs to. Okay.
Yes.
And how do you see that how xz will transform? You can just multiply the
See.
uh, these two symmetry species, and you are going to lead to 1 minus 1 1 1. So 1 minus 1 1 minus 1. So xz is going to be same as x, yz is also going to
Z
be
is
same
equal
as,
to I, and Z
yes.
is identical operation. That's why X will
No, no,
become X.
not identical, the term is totally symmetric.
Identity. Yes, totally symmetric. Yes, totally
Totally
symmetric.
symmetric.
Yes.
Okay. And also you take x square, y square, z square, so they will all become totally symmetric, right? Okay. Now for C3b, we also we can also do the same thing. The total number of symmetry operations are 6, but the total number of class is here are 3, because 3, so your C3 operations are equivalent. Sigma V operations are equivalent. So that's why number of class is 3. So number of irreducible representation is 3. So by that, acha, here I have some other, acha. Now you know how to form the character table, right? And by
Yes.
character table, by constructing the character table and by Mulliken nomenclature, you can name and form the irreducible representation for a group. Now suppose you are given a reducible representation and you need to break it down into irreducible representation. So by name itself, that the each of the reducible representation can be broken down into irreducible representation.
Yes.
How can
We
you do
suppose
it?
by
How can you
similarity
do it?
transform.
By similarity transformation. But
Yes.
let me give you some. This is the shortcut method we are going to use. Similarity transformation is going to be very long method, and this is just the actually what I can say. This is the means output of that similarity transform only, but in a simple fashion. And you have already, I think, used it maybe. Just I am
Yes.
going to give you the derivation only. And these
Yes.
all the derivations are available in Cotton's book, F.A. Cotton. Okay, that
Okay.
is a symmetry and group theory by F.A. Cotton. You can find it in online, I guess. Even you can buy it. This is a very good book. This is, I think, a Bible for symmetry and group theory now that has been considered. So now suppose you have a reducible representation and you have irreducible representation. And now this is your GOT. These are the two rules we are going to use. So suppose this is your sum over R. Now character of the reducible representation multiply by character of the ith irreducible representation of the same symmetry operation. And you are going to take a sum over R. But before that, I should say this, that your reducible representation, as we have discussed, this is a sum of all the possible, not all, but possible reducible, irreducible representation, right? Suppose
Yes.
we can I write it like this: sum over j, aj, gamma j. Gamma j is are the gamma j can be the irreducible representation. So, and why did I multiply with aj? how many times gamma j is appearing in your reducible representation. So gamma j can come once, gamma j come twice, and even gamma j come none of the time. So aj can be 0, aj can be any multiple, any integer. Okay, but it cannot be decimal.
Yeah.
It can be only integer starting from 0 to n. So now think of a particular symmetry operation and character of the transformational matrix of that. Can we write the next line? This one. That character of R, I have just written the same thing. Sum over J, AJ, character of R
Right.
of the
Right.
jth irreducible representation. Okay. So I can write this. So now what I was writing this sum over R, character of R, character of ith, character of R in ith irreducible representation. So I can break it down the first chi of R in this sum over R is same, but look that instead of chi R, I am writing sum over J AJ character of R in the jth irreducible representation multiplied by
Right. Right.
chi of R in
I.
ith irreducible representation. See what are the variables here? Obviously, the symmetry operation is there, different symmetry operation sum over R. But now we are going to think only in terms of J. So what are the possibilities? I can be equals to J,
Yes.
and I can be J can be anything other than I. Okay. So what will happen when J will not be equals to I? That time it is going to follow the second equation, this equation, orthogonality one.
Mm. Yes.
So I is not equals to J. Then those sum, so this is sum over J. So suppose it is A1, chi 1 and chi R, chi I. So they may not be equal. So that will be 0. When they are going to equal, that is going to give me H,
Order of the. Yes.
order of the group. Now let me show you the next line. See, sum over R, A1, chi 1, chi I, A2, chi 2, R. But don't forget the sum over R. Sum over R is there. Okay. Even you can take a bracket here. Sum of R you can write only once. I hope you are getting my point.
Yes.
Now
Yes. Yes.
see, each of them are going to be 0 other than
Except.
this,
Except. Yes. I.
other than j equals to I.
Yes.
All of them are going to be equal.
Yes.
So ultimately see, this is going to give me that sum over R chi R into chi I of R is AIH. Why H is there? Now AI was here, right?
Yes.
So that is going to give me AI into H. Actually, I should not have written this R these many times. I should have taken a bracket here. That is, I think, of a wrong writing. So you can take only sum over R once, and you can take this inside the sum. So that is going to give you only the AIH. Okay,
Yes.
and how can so now you wanted to know that how many times this irreducible representation is going to appear in this reducible representation. That can be given that AI can be written in terms of 1 over h sum over r character of the symmetry operation in the reducible representation multiplied by character of the symmetry operation in the irreducible representation. That's how you can get the AI. Actually, why this is important, you are going to face this in the upcoming uh, courses. I think you have already looked at the week 8 literature, right? Where normal modes of vibration or those kind of, I think it is discussed, right?
Yes, yes. In the
So
eight, yes, assignment, eighth week
assignment,
assignment. Yes, they have given
yes.
this kind of
So
problem.
yes, so there you are going to require this, and so you can take this axiomatically, but you also you have the idea that how this actually you are getting this formula. If you forget sometime, you can always remember by this. Anyway,
Yes,
from here, what we are understanding is how many number of times the ith irreducible representation is going to appear in the reducible representation. So we are going to solve some numerical based on that, but because before that, let us solve some assignment 6 problems. Okay. So first problem D2H molecule. Can you tell me a D2H molecule? Which molecule can have D2H? It should have some molecular plane. It should have
DC, yes,
C2 as
double
a C2 as a molecular plane.
bond. C2H4 is the molecule.
What C2?
H4. Yes,
C2H4.
yes.
C2 to C H are there. Now, yes, C2H4 means ethane. Sorry, ethene.
Ethane.
Ethene. Uh,
Yes, yes.
if it is ethane, then it is
No, no, no. Yes,
C2H6.
yes,
It
yes.
is ethene.
Ethane.
So that is a D2H molecule. Now consider the principal axis to be along the Z direction. First of all, if you think of it as a uh, uh, C2, suppose you already told me the ethene molecule, right? What do you think where the C2 is there?
This
Principal axis,
C2 is passing through the double bond.
double
Or
bond.
maybe, yes, yes.
Why not the molecular plane?
Yes, it can pass through molecular plane also.
Yes, I think there is a, I don't know if the notion is correct or not, that sometimes it is said that the principal axis, so suppose you have multiple C2, okay, how to
Yes.
identify which C2 is your principal axis?
Okay.
So if your molecular plane is there, then you take the Z axis perpendicular to that only,
Molecular. Okay.
like for ethane. Sometimes it is also someone can say that the principal axis should contain maximum number of atoms. But I don't think that is a correct notion. If it would have the correct thing, then the ethene could not have the molecular plane, right?
Yes.
If the C2 is perpendicular to the double bond, then you see your molecular plane, it had a molecular plane, but it is not XY anymore.
Mm.
It has become, it has Z axis. It has become a vertical plane, right?
Yes.
So you need to take the Z axis uh, perpendicular to the molecular plane. So, but for this problem, so I have just discussed this to clear the basics. But see, this problem, what they are saying, that take the principal axis to be along z direction using the unit vectors along these three Cartesian as basis, means x, y, z as basis. A resultant symmetry of the operations. This is a product of symmetry operation sigma xy and
C2X.
c2x over xyz. So for this kind of problem, you have to take it from the C2x, then so transform your xyz with C2x first and then sigma xy. What I'm trying to say, this is remaining as it is. And when you change C2x for
X will remain as
xyz,
same.
your x remain the same.
Yes.
This
Minus by
actually
minus.
changes. Yes. Now, what about your when sigma xy will work on this? Your
Only
xy
Z.
are going to be invariant.
Yes,
So
yes. Only
it,
Z will change the sign.
z become
Yes,
positive. So
yes.
what is this equivalent to? So
Sigma
say
ZX.
suppose xyz, what operation you do to get x minus yz? So
Sigma
your
ZX.
x and z should not change, only y. So it is
Only Y. Sigma ZX.
zx. So this is the correct option. Okay.
Yes.
Now the second question. Consider the carbonate ion CO3 minus the one I just told you. So your carbon is there in the center and these are the three oxygens. Okay. Now these three oxygen atoms are designated as 1, 2 and 3 and carbon is designated as 4. Now they are saying taking pz axis for the oxygen atoms, the basis set becomes pz1, pz2, pz3. Okay. Only the pz axis because your z axis is along this and that's why they have given you the pz orbital only. So you have the idea of the orbitals, right? Yeah,
Yes.
Soumitra,
Yes.
that
Yes. Yes.
how the pz or px or py will look like
Yes. Yes.
dumbbell shape, right?
Yes.
A dumbbell shape was actually not true. Both the lobes are actually circular, spherical. I should say the distribution function. If you look from the angle of quantum mechanics, we used
Okay.
to say like the dumbbell kind of shape, but actually yes, dumbbell, but spherical, not like this, not like elliptical one. So these are spherical. Anyway, that doesn't change the, and those have two different lobes, means two different phases. So one darker and one lighter. So along the z-axis, positive z-axis, the lobe is darker, and the another axis it is lighter one, along minus z. So see, now we have the transformational matrix. Transformational matrix is given 0, 1, 0, 1, 0, 0, 0, 0, 1. So let us write it once. 0, 1, 0, 1, 0, 0, and 0, 0, 1. So this is what is the dimensionality? 3 into 3. Now
Yes.
we will multiply with our basis set Pz1, Pz2, Pz3. So they could have taken any of the orbitals, but for this particular problem, they have taken these three of the oxygen only, not the carbon. Okay, so they can form the basis set any way you want. Okay, now this is what is the dimension of this matrix? 3 into 1. 3
Yes.
rows, 1 column.
Yes. 3 cross 1. Three
So
cross
what do you think the product is going to be?
3 cross 1. 3 by 1.
3 by 1,
By 1.
right? Okay. How do we do that? The 3 into 3, 3 rows, 3 column, and then 3 rows, 1 column. So we just think of it
Resolve this inner 3.
3 into 1, right? And
Yes.
what is the, so for once I will do the, and it is as it is simple, I will do it. 0 into Pg1 plus 1 into Pg2
Yes.
plus
0
0
into PG.
into
PG3.
Pg3. Same here, 1 into Pg1. So you take this, multiply along the row, along the column. 0 into Pg2 plus 0 into Pg3. So far, next will be 0 plus 0 into 1 into Pg3. So ultimately what we are going to get? Pg2, Pg1 and Pg3. So what we can see that the for 3 it has not changed.
Yes,
It has
means
remained
no
as it is. But the for the other one, it has not it has changed the position. 1 becomes 2, 2 becomes 1. So we must have performed some experiment, some operation that 1 has become 2 and 2 has become 1, but 3 hasn't changed its position. So
YZ plane is there.
it cannot be a rotation, right?
Yes,
If you rotate, then your what could have happened if you rotated along the z-axis? So let us go one by one. These four options are there. Let us go one by one. So C3 along Z. So if we would have rotated it along C3, then 2 has become 1, 1 would have become 3, 3 would have become 1, 1 would have become 2, and 2 would have become 3. But
yes,
that is not the case here. So it is not an option. What about C2 along Y? So along Y, if you had done a C2 along Y, then what would have happened? That 2 has become 1, 1 has become 2, but what else could
three.
have happened?
Yes,
That your C2 has become 1. The
but the lobes will change the sign. Means this
yeah,
upper, yes, upper lobe will become lower and lower will be changed sign.
yes, right?
Because
So
yes,
it would
because
have become
four and
minus,
three are on, yes, yes, because four and three molecules are on the same line at
right?
y-axis. Yes,
Right.
they will not replace, they will not go anywhere. They will remain unchanged.
But lobes are going to change.
Yes,
And
yes,
then, as we are discussing about the PZ axis, so uh, PZ would have become PZ3 would have become minus PZ3.
yes,
P2 PZ2 would have become minus PZ1.
yes, yes,
Okay. Now, what would have happened if we would have used a molecular plane? All would have become the same. 2 become 2, 1 become 1, 3 become 3, but minus because lobes
changes
are
sign.
going to change, right? So this is
Yes,
also not the correct answer. So only the correct answer is sigma b along the yz axis. Then you can see your none of the lobes are changed, but your this 3 becomes 3 because the yz will just make into half, but half along the z axis,
yes,
sorry, half along the y-axis, so it doesn't matter. But 2 becomes 1 and 1 becomes 2 along that reflection axis. So this is the correct answer. Okay, now let us go to the next questions. The question number 3, the product of C2x and C2y. Same, so you will tell me, just let me,
C to Z.
oh, no, not like that. You have to tell me from here.
Yes, okay. Then it will become minus x minus y.
So C2x
X into minus x minus y. Minus x, y into minus x. Sir. Yes,
because
minus.
yes, now
Now it will become minus x. This will become minus y and z. So
so
it will become c to z.
C2, this is the correct answer, right? Okay.
Yes.
Now the next question. I don't actually I also don't have idea. Can you tell me a group of order 4, what is going to be the answer and what is the correct uh, justification?
It is commutative. It is the condition of a group. So it
Hmm.
is right. One option will be commutative, and the second option may be cyclic or may not be cyclic. Means maybe cyclic or acyclic.
When a group is called cyclic.
Means repeated operation will produce the other EA. Means let's say 1 omega omega square kind of group. Means if you operate once again, then it will produce the another element of the group.
Yes. Um, what are the can C3 is a cyclic group?
C3. C3. I don't think so. C3.
C3 can produce C23,
Yes.
and C23 can produce C33, which is identity itself. So if your point group itself is C3, because there is no other symmetry operations, no sigma V, no sigma H, nothing.
Yes, yes, yes. C3
So
is a cyclic.
then
C3
C3
can
would be a
produce.
cyclic.
Yes,
So
C3.
so first of all, it is always so if there is only one option and you know that the uh,
Commutative.
commutative is going to be the answer because that's what a group is called. The definition of a group, it should have been commutative.
Yes.
So you can, if it is MCQ kind of answer, then obviously you go for the first one. It is not necessarily cyclic, not necessarily acyclic. Can be either cyclic, can be acyclic.
Yes.
Don't have to go for those.
Yes.
Okay. Number five. This is about the Raman scattering. Why are laser sources are ideal for excitation in experiments dealing with Raman scattering? I think there are multiple answers associated with
Yes. Yes. I choose high intensity,
it. Hmm.
and they provided this monochromatic, this
Actually,
highly monochromatic.
both of them are going to be correct.
Yes. Yes.
Did they correct it for? I think yesterday some mail came.
Yes. Yes.
I think they have. I don't think they have corrected it. Let me check. Question 4 of assignment 6. Only D. How can it be possible? Oh, question 4 is D. Achha, achha. Question 5 they have not discussed. So I'll also tell them to change this. Okay. Now, why high intensity? Because here you are dealing with. You remember why you need a high intensity?
Yes. Because
Why?
your A is very feeble. Means in the Raman's A, your
Hmm.
this electric field must interact with this quadrupole moment. It
Right.
must have.
Right. Yeah, what should I say? It's not a dipole-dipole interaction. It is a
Yes. Yes. Yes.
induced
Quadrupole.
dipole-induced dipole
Yes.
kind of
Yes. Yes.
interaction. So for that, we need a higher value of electric field, and that's why that can be coming from a high intensity. Okay. And why do you need monochromaticity?
It's always preferred to be monochromatic with single CCA.
Right. Right. Then question number 6. Combinations which have a group and subgroup. Means, suppose, what do you think? Did you opt for this question?
I just gave randomly this C4V and C2V.
And you got the correct answer?
I didn't check.
I think that is one of the correct answer. So, what is actually there? Is see what is so in this combination, the first option is the bigger group,
Yes.
and the second, the after the comma, it's subgroup. Subgroup means OH character tables can contain the C3b. Okay, so that's when it is called a group and subgroup. So if you now let me go to this. I told you about this earlier, right? The symmetry Jacobs University.de. Let us go to octahedral one. Okay.
Yes.
So in octahedral one, you will see that these operations actually the subgroups are given here. See, a octahedral group can have these many subgroups
Yes. Yes.
upon which you can see C3b and C4b are there.
Okay.
So first two options are definitely correct.
Okay.
C3b and C4b. What about C4v and C2v? Let us check. C4V, right?
Yes.
C4V, C4V. Subgroups of C4V, C2, C2, C4,
Yes.
C2V. So it's correct. All the
Yes.
three are correct. Not all the three. This one. But C4V can't have C3V because
Mm.
C4V cannot have C3, right?
Yes. Yes.
So the cyclic group along the following we have just discussed C3, right?
See.
Now week 7 assignment as it actually easy, right? Let us do
Yes.
this. Sum of the square of the dimension of all the irreducible representation. So sum of
On
square of the all of the irreducible dimension. Square of dimension means Li square
square summation over
summation over I
I.
guess. So this is
H.
your H.
H.
So it's order, right?
Yes.
Not the classes, not the number, not the number of atoms in the molecule. Okay. Now the question is ClF3 molecule, the point group of ClF3 molecule and its corresponding irreducible representation. First, let us see how the ClF3 will look like. It is actually a T-shaped planar molecule. I
Okay.
should not say planar. This is in plane. Now there are two. This is not actually a planar molecule. These lone pairs are there in two different directions. But let us see. Huh? Now I have drawn it in a plane, but it is not actually similar to. See, you can think of it as a NH3 molecule. Huh? Let me give you that idea only. Okay.
Yes.
Now obviously C3 is there,
Yes.
E is there, C3 is there.
C3. I don't think so. C3 is there.
C3 is not there.
Yes.
Why do you think so?
Not planar. That's why. Sorry.
Oh, sorry. Actually this is a planar molecule. I'm sorry. I'm sorry. Not planar. Sorry. The thing is, it doesn't have C3 not because of the.
Yes.
Why do you say it doesn't have C3?
It's like a seesaw kind of this F to F like a seesaw. I think so.
Yes,
Seesaw kind
because actually because of the lone pairs it
of
cannot have
don't
C3,
yes, yes, yes.
but it can have a C2, right?
Yes.
Along along one of the bond.
Yes, this lone pair along this lone pair. Lone pair F, CLF and containing the lone pair.
Which one? Tell me.
This CLF and lone pair along this line. CLF
Along
and
this
lone.
line it can have.
Yes.
No, not that. Is that the one or the one that's coming towards me? Like this?
Look,
Actually, the lone pairs, I think they are on the two different sides. So if you think it like this, then what is actually happening when you are rotating, these become this. Actually, um, you can think of something like these two are there. Now, upon a C2 along this, suppose this is my Z and C2, then what will happen? This will come here, this will go there, F will remain at its position, and
yes.
this will come to here. So C2 is there. So is there any perpendicular C2 are there or not? There are not because of this lone pair. So no perpendicular C2s. What about sigma V?
Sigma B will be there.
Sigma
Sigma
V's
B
are
will be
there.
yes.
So how many sigma V's are there?
One is
each along the bonds. Let me actually check the structure. Do we have the structure of ClF3? Chlorine trifluoride have a T-shaped molecular geometry. The central chlorine atom undergo sp3d hybridization like this. Acha, they have the structure like this. So you have drawn a little wrong, but the thing is same. Along this, if you have a C2 axis, then this they are going to interchange. So the way I have drawn it was correct, I guess. Let me draw it again. Maybe I need to delete this. First of all, we got this correct, right? What about this? This is here. These are your AFH fluorine. Now you can have C2 along this, right? It will
yes,
become this and like this, and these are the sigma V's are along individual fluorines. So
yes,
not all. I don't think they have only two sigma V, not three sigma V's, right? Let us go back to the structure once more here. So one sigma V along the same plane, right?
yes, yes.
And another will be containing this fluorine, this fluorine, and these two lone pairs also, or not? No.
No, they are
Then it
not in the
would,
same line. Yes.
yes. Then what is the another plane? What do you think? So this is the structure they are saying. See, this is the structure. The lone pair, one of the lone pair is there, another lone pair is there. These are the three F. So your C2 is fine, and another C2 is also see another one of the sigma V is along this,
Yes.
right?
Yes. Yes.
Acha, another would contain all of these three fluorine and also the chlorine.
Yeah.
You got my point. So one of the sigma V will contain only the chlorine and one fluorine, and
Okay.
another
Yes.
will contain all the three fluorines and chlorine, and it will dissect along these two lone pairs.
Okay.
So it is two sigma V planes are also there. So let us come back here. What do we have? If I draw it in their fashion, so F, F, then we have basically two lone pairs. Okay, so it has E, it has C2, Z, it has C2, sorry, sigma V. So that is so first sigma V has all the three F. It contains three Fs, one of them. Another sigma V contain chlorine and only one of the fluorine. Okay, so it is
Yes.
actually C2V point group. So out of this, there are two C2V, and you know if it is C2V, then what? How many classes are there?
Four classes.
Four classes. So if four classes, then how many irreducible representation?
Four.
Four. So this is the correct answer. Now question number three. Matrix element behave like a set of orthonormal vectors for reducible only, for irreducible, for reducible as well as irreducible, one dimensional irreducible representation. What do you think? This is a good question.
for irreducible representation.
For irreducible representation. Why don't you think it will also work for a reducible representations?
Uh,
As they
Reducible,
contain as they contain the same uh, irreducible representations.
they contains, but they can be ultimately reduced. No,
Yes, means what I
you
am
are
trying to
asking
say.
why
Suppose this is reducible representation. I can
yes,
write it in terms of J, AJ, gamma J.
yes,
Sorry. So this is irreducible representation. This is my reducible representation.
yes,
So I can write a irreducible. So that I am not arguing that we can obviously do it for irreducible, but can we not do it for reducible representations as well as the orthonormal vectors? Because you see, our reducible representation is nothing but a sum of irreducible representations.
yes,
So, so when we break into it, then it become orthonormal again.
yes,
So see, the options are irreducible, but not irreducible representation. So that is not correct. Again, reducible but not irreducible representation. That is the even not correct. One
one
dimensional
time
irreducible representation.
that is the correct option.
That is correct option. Uh, Actually, that is the correct option. But similarly, reducible as well as irreducible representation. These two actually are correct answer. I guess should have been. And this should have been two is multiple correct answer, not MCQ. Okay, I will check with them again, and then let us come back to question number four. We have to give a Mulligan nomenclature of that. First of all, what is the character of the identity operation?
Pardon.
Can you tell me the identity operation character of the identity operation?
One, one, one.
One. So
Yes.
it could be either A or B. Obviously, that is there are only A and B options are there. Now tell me about the uh, second one. What is the principal axis? C3, right? So according to C3, it is symmetric. So
Yes.
it is A1.
A1. Yes.
Oh
And
no, sorry.
you are
It is A.
yes.
Now it is A. Up to
Yes.
the, it could have been A or B up to this.
Yes.
From here it is A. Now
Yes.
the next symmetry operation, it is symmetric with respect to that. Now it is A1.
Yes.
Now
G. It
point of
is I.
inversion, it is
G.
symmetric. So A1G.
Yes.
So that is the option is there. So it is A1G.
Yeah. Yes.
Now question number five. A two-dimensional representation may have a character with the value of. Do you remember the which two-dimensional representation you can remember?
Which dimension? This
Which
in the case of C3 there I think in the case of C
C3V, C3V.
yes C3
So there it had -1 and 0.
yes
I think all the
it can
four should
take
have been
yes
correct.
yes it can take also imaginary values also
It could be one, it could be
yes
so. I think all the four options should have been correct.
yes yes
But I think they have went only with C and D. I think all the four options should have been correct. Anyway, now let us go to uh, question number six. For the and just wait, I need to pick up a call. Yes. मैक्सिमम सारे वो कॉर्नर में चले गए थे ना कोशिश करो लाइट कॉर्नर में लिए होंगे ठीक है ओके कल बोलो सबको लेके चले जाओ और प्लॉट करना है अच्छे से बंद करना नहीं मैं पढ़ा रहा हूँ sorry I was guiding my one of our MSc student. Anyway, so for irreducible representation, the question number six, let us come back. We have to determine the Mulliken nomenclature of the representation, irreducible representation. So let us start with the identity. It is B, right? Because
Yes.
the dimensionality is two. Now it is antisymmetric with respect to C3. So what it should have been?
E or B, that is one dimensional. No, sorry.
Hmm?
E or B,
Oh,
that is
sorry,
one
sorry,
dimensional.
sorry, sorry. It should have been E, right?
Yes.
Good. Now, with respect to C3, it is antisymmetric. So, what should I write? E what?
Two.
E2. Then, so there are no other options. So, this is correct, right?
Yes.
Okay. Now, these are the questions where we require that formula that I have. Obviously, you can get it by similarity transformation. That the question is deconvolute the following reducible representation into irreducible ones. Representation or reducible representation gamma as sum of irreducible one means so your irreducible representation is given. You need to see that what are the constituent irreducible representations are there and your character table is given. Okay, so
Okay.
we will do the hardest one, the tetrahedral one,
Yes.
and you need to do the rest of the three. Is it a fair deal?
Yeah, yeah.
Okay. So let us go to the last one, TD. Obviously, tetrahedral contains much more other. I think tetrahedral, if we see the character table, the whole character table, let us see once. No, they contain these only, these many. So this many. So this is the character. Actually, let me actually give you the correct thing. I think I have done some problem. Maybe for this also you will require that. So you will, I hope you will try to solve them.
Yes, sure. Sure.
Okay. Now let us come back to this. So this is our reducible representation. And we know the formula that our AI is going to be what? Can you tell me?
1 over H,
1 over H
summation over R,
summation over R
chi R, chi R, I R,
I R
I
of
I.
huh,
This is chi I. Yes.
good. Now let us start with, so this is our reducible representation. So it tells me that E7 for C3, 1, these are the things. So let us start that how many and what are the for tetrahedral C. As we have it, let us discuss it once. So you can see what are the symmetry operations possible. Identity C3, 8 C3, 3 C2 operations, 6 S4 operations, and 6 sigma D dihedral planes are also there. Okay. So how many total so what is the total number of operations and H?
Yes. 12 plus 18, 20, 24.
1 plus 8 plus 3 plus 6 plus 6. 9 and 3, 12, 12 and 12, 24. Right?
Yes.
And total number of classes are 1, 2, 3, 4, 5. So 5 classes, 5 symmetry elements.
Yes.
Upon which there are two one-dimensional, one two-dimensional, and two three-dimensional
Three.
irreducible representations are. When we look at the basis set, we can see that x, y, z, they transform together with T2. For Rx, Ry, Rz, these are the rotation along x, y, z. So that of that what's so rotational kind of rotational. So these Rx, Ry, Rz, they transform together again along T1. And can you tell
Yes.
me why this? What do we mean by this character as zero?
Zero means when they are nullifying one each means one operation is nullified by the other.
Yes, that means the contribution is zero uh, because they are transforming together. And by
Yes.
transforming together, what they are doing, they may be nullifying the contribution from each other.
Yes. Yes.
It is not annihilation operator
Yes.
anyway.
Yes.
So they it is actually transforming. Okay. Now now we have 1 over h we know. Now let us start with how many A1s are there. So 1 over 24, and then we will first start with identity. Chi of identity is 1. Acha, let me take the first as the 7 of the irreducible reduction, then 1. Then then what should I take? Then for C3, tell me what should I write?
8 into 7 into 7 into 8 into
7 into 8. Or I should write 8 first.
okay.
N, let me write it first, and then 1. Why I have written 8?
These are equivalent operations are there, no? These 8
Yes.
C3s are
So actually there are 8 C3 operations. So we need to do for all the 8. So that's why we are multiplying with it. Here in the equation it is not written.
Yes.
because they are all different symmetry operations. But these different 8 C3 different operations are actually equivalent. So that's why we are multiplying with 8. But in the equation it is not there, so you should not miss it. So next should be 3 into minus 1 from irreducible and plus 1 here. Then 6 into
Then 7, whether you have to multiply or not, sir.
7. Which 7? I
You are
did.
considering yes, this first time, first 7 into 1 you do. Then in the second case you do 8 into 7 into 1.
Oh, sorry, 8 into 1 it should have been. 1 from this.
Yes.
Then 6 into S4. 6 into minus 1 into 1 plus 6 into minus 1 into 1. This is 1 over 24 into 7 plus 8 minus 3 minus 6 minus 6. Right?
0.
Huh? So it is 15
0.
minus
0.
15. So 0. There is no A1 is not there. What about A2? 1 over 24. Then what are the things there? 7 into 1, 8 into 1 into 1 plus 3 into minus 1 into 1 plus 6 into minus 1 into minus 1 plus 6 into minus 1 into minus 1 over 24 into 7 plus 8 minus 3 plus 6 plus 6. So 15 minus 3, 12. 12 plus 12
1.
for
1.
24. So it will
Yes.
appear once. What about E? 1 over 24, 7 into 1 plus 7 into 1, not 1, 7 into 2, right? 7 into 2,
2.
8 into 1 into minus 1 plus 3 into minus 1 into plus 2. Then we are multiplying by 0. So 0
Yes.
plus 0. So this is 1 over 24 into 14 minus 8 minus 6. So this is also 0. So there is no E. What about T1? 1 over 24, 7 into 3 plus 0 plus 3 into minus 1 into minus 1 plus 6 into minus 1 into 1, then 6 into minus 1 into plus 1, or no, into minus. So it will become 1 over 24 into 21 plus
Then
3
plus 3 minus
minus
6.
6 plus 6. So they
1. It will
24 1. What about T2? Same, 7 into 3 plus 0 plus 3 into minus 1 into same, actually almost. So here the change is there. 6 into minus 1 into minus 1 plus 6 into minus 1 into plus 1. Same, it will give you 1. So ultimately let me give you in another color that your gamma RR is A2 plus T1 plus T2.
Yes.
Do you agree?
Yes, yes, sir. Totally agree with you.
So you need to do this for the rest of the two,
Yes, yes,
and this D2D, C3B and D2. You
yes,
do this for, and then on the next class we'll start with the normal modes of vibration and associated numerical problems. So maybe with this we can stop today's session.
yes.
Uh, I hope this. So you already knew these things, but I hope this derivation give
Yes,
you
yes.
some
This kind of
flavors.
this molecular symmetry is newer to me, but I have
Hmm.
done this group theory. I have already read in my MSc during my MSc courses on this thing. But this molecular symmetry is newer.
Yes. So how to get the point groups and all? I would suggest you can look at Atkins' book. Do you have a e-copy or some copy of Atkins' book?
Yes, yes, yes,
So in Atkins' book also they have very nice examples of molecules. Or even I told you this website, right? You can even go to this one. I have opened it. Symmetry.otterwine something. So there, how can you commit here? You can see symmetry otterwine. You go there. Then you go to the um uh, space group. No, the tutorials. Even here in tutorial, you look at the gallery. So in gallery, you have different molecules. C1, suppose you have written C1, so you can visualize the molecule. So it has only identity operation.
yes, yes.
When you select this, I think it will show you. I don't know why it's not. Maybe we can look at C1. These are all C1. What is the difference between C1 and CS? Acha, in CS, there is sigma H, only sigma H, the molecular plane.
Molecular claims.
So this is Br2, not Br2, ethylene, Br, and CN. Okay, and see, this is the molecular plane. That's
Yes,
how we can visualize. Then Ci means obviously instead of sigma H, there is a
quantum inversion.
yeah, yes, point of inversion is there, and that is this along this. Let us see carbon dioxide. See,
Yes,
carbon dioxide.
yes,
The- So first of all, you can see it is not really a. So see, this is a sigma C infinity.
C
That
infinity. Yes,
means along this bond, so along this, you can rotate one, two, three, anything. Infinite angles are possible where you
yes,
are getting the equivalent structure. That's why C infinity.
yes, yes,
Now, that's why C infinity. Now, with the same vertical C, those many CNs, you are going to get that many infinite number of sigma V also. So
yes, yes,
like this kind of a cylinder. So
yes,
each of the slice of this cylinder are that each of the individual sigma V planes.
yes,
Now uh, obviously it has an inversion along the oxygen
yes,
and also the two improper S infinities. Okay.
yes,
Why? Where are the two? One, acha, one is uh, your one of them, and another is the inverse one. And what about C2 dash? So they have these also.
Infinities.
Yes. So n number of C2 perpendicular to I should say infinite number of C2 dash. Okay.
Yes.
See this infinite number of C2 dash.
Rotation space. Yes.
Yes. But there is the sigma sigma h. You can't see sigma h because your see this is along this.
Yes.
What about acetylene? What is the difference in acetylene? Let us see where the C infinity is same, sigma
Yes.
v is same, inversion is there.
Yes.
You have the same thing. Then why it is d sigma is and um,
D.
that is oh no, both are carbon dioxide and uh,
Yes. The D
both
sigma.
are
D.
d sigma h because
D.
of
Very.
the n number of perpendicular C2 axis.
Yes. Yes.
Because of this,
In-
sigma V is hydrogen cyanide, po- polyatomic,
Yes.
sorry, heteroatomic. This
No,
tri
inversion center is there. Inversion center is not
inversion
there.
center is also not there, and there are no C2 axis perpendicular to the sigma infinities are not there.
Yes. Yes.
Okay, okay. Now let us see some cyclic C2 hydrogen peroxide. So like this, you can.
Yes,
That's
sir.
what I'm trying to say. Let
I'll visit this site, sir.
yes,
Yes.
yes. Let us see the d sigma h we are talking about. Na? Let us see that ethylene. I want to see that where the C2Z is actually going. Acha, see, that is what I was saying, that it is not going through the more number of atoms. It is perpendicular to the sigma h. Okay. So like this, you can check this website to see different molecules. You can go to the gallery, and in gallery option, you can get the options. Even you can get some tutorial problems. You can some they will give you maybe uh, questions. These molecule they have given, then they are asking, does this molecule have an infinite rotation of axis? What do you
Yes.
think? You can always opt. Huh?
Yes.
I
Yes.
don't think yes. And no is the correct answer, yes. And does this molecule have C3? You need to look it. Okay. Then select the highest order of Cn possible. I think C2. I'm not sure if I have given the correct answer. Are there two C2 axis perpendicular to does this molecular contain okay, one by one questions are coming. I'm not sure if I'm giving the correct answer. Does the molecule contains two dihedral bonds? But you check it yourself, huh? Okay.
Yes, sir.
Now let us actually stop today's session. Stop presenting. And thank you for joining, Soumitra. I
Thank you.
hope to
Thank
see you on the Monday with the
you.
next
Sure.
set of questions. Try to solve the irreducible representations into the
Sure.
deconvolute them into irreducible representation, and we'll meet soon. Okay,
Sure.
so good night. See you
Sure.
soon.